Hello everyone, welcome back to my channel. Today we want to make a spectrum analyzer using ADALM Pluto. For that, I just thought to first just describe what are the approaches we can take to create a spectrum analyzer. Then we go to the code. First, let's say we have a signal at our receiver which has a frequency content around 2.4 gigahertz within the 10 megahertz bandwidth, right? So we want to see what's the spectrum of this received signal. We can take two approaches. One is uh, in our receiver, set the LO frequency of the RX equal to this 2.4. What happens when we do that after the signal is downmixed, we get this baseband signal. The center frequency becomes 0 megahertz, and then we have the baseband has this shape. Now that the signal is in low frequency baseband region, our ADC can read and convert this signal from analog domain to digital. And we can use this in our Pluto to read back the ADC data and convert that information from time domain to frequency domain by taking an FFT, which is a fast Fourier transform. As you know, a spectrum is the information of the signal in frequency domain. So for that, we need to use Fourier transform to convert our signal from time domain to frequency domain. And especially for dealing with uh, digital sample signal that are from output of ADC, we can use FFT, which is the fast Fourier transform to take the get the frequency content. This is the first approach which we will going to take in this video. Now you can see that after down conversion, this 2.4 is centered at 0, and when we take the fast Fourier transform, we can get the shape of the spectrum in frequency domain. But there is another approach. We can say, what if we don't want to take the Fourier transform? Um, there is the second approach is the approach that usually is used in a spectrum analyzers, which is by sweeping the LO frequency within pre, like for instance in our spectrum analyzer we say search from 1 gigahertz to 3 gigahertz. So we sweep the LO frequency from 1 gigahertz to 3 gigahertz with steps of 1 megahertz. Then at each step, when we set the frequency, the LO frequency, we calculate the power after the down mixing. What happens is that essentially what we do here is that when we are sweeping every 1 megahertz steps, we are measuring the power of the signal at that frequency. Let me illustrate here. I say start sweep. We are starting from 1.8 to 3 gigahertz here. Right now, we are just measuring noise. But once we approach this area, 2.4 gigahertz, every 100 megahertz that we are sweeping, we can see some power which gives us the spectrum at the receiver. And you can see one issue with this approach. One is we need very fine steps if we want to get a spectrum with very good frequency resolution. For instance, I set the step in such a way here that because right now here we have very sharp transition in this frequency, although may not be something we encounter with in real applications. But let's say we have some sharp behavior. If our frequency steps are not fine enough, we may see this as a ramp or a slowed down behavior. Also, our LO frequency needs to give us the ability to tune its frequency content with fine steps. This is also something that may complicate the design of PLL. Um, Usually for these things, when we want to have very fine frequency steps, we need to use fractional PLLs that normally their frequency resolution or their frequency steps are limited to the architecture of that PLL number of like how many counters we have or how many bits we have for defining the division, and also how well is the phase noise of the oscillator. If the phase noise of the oscillator is not low enough, we may not be able to get very fine frequency steps from that LO. To, After this, so first, in this video, we are going to go for the second approach, but in another video, we are going to also uh, implement the third approach. The third approach also sometimes for some applications is used to create a lock-in amplifier. A lock-in amplifier is a tool that in very noisy environment gives us the ability to look at a very specific frequency in the received signal so we can just avoid all other noise sources. Before moving on to working with Python code, I just want to mention how to set up the required libraries and drivers to be able to interact with ADALM Pluto. The first one is the library for Windows or Windows that you can download from GitHub. It's provided from Analog Devices. You need to download and install this driver so your ADAM Pluto is uh, defined and recognized correctly by Windows. Also, you need a library, I think it's libio, to interact with different SDR ICs of analog devices in Python. Um, when you go to these GitHub pages, you can access the latest releases. Um, Also, these drivers are available for other operating systems, Linux or Mac. This website, I put the link down in the description. If you go there, there is a very good uh, uh, instruction to how to install the drivers for different operating systems and also very useful information about SDRs in general. So I strongly suggest that you can also visit this website. Okay, now let's look at the code. So here, as I mentioned, you need the libio library to interact with analog devices SDR ICs. For that, you just need to import ADI library. There are also in that GitHub page that I mentioned earlier, there are other examples for different SDR ICs that you can go and take a look at. Just now that we have the library, we just need to connect to our SDR. Um, we need to say ADI.AD9361, which is the IC inside our Pluto, and give the IP address, which is the IP address that uh, device has once it gets connected to our PC. Now we can get connected to the SDR. After that, we need to configure our RX and TX info. We have the sample rate. In this example, I have set it to 30 megahertz. The center frequency, as I mentioned, for this approach, the RX LO and TXLO both need to be equal to center frequency. In this case, I have set it to 2.25 gigahertz. Number of sample is how much is the ADC buffer, how many sample points ADC reads every time that we read the RX data. In this example, I set it to 8 multiplied by 4,000. The bandwidth is the RF bandwidth of the filters you have in your TX chain or your RX chain, which I set equal to our sample rate. One more thing which I talk more in the future videos, because by default, ADALM Pluto comes with only one TX and one RX channel enabled. But you can modify the firmware of the IC inside ADALM Pluto and unlock the second channel. Not only that, you can unlock the frequency range of the LO. And that's for future videos, but because right now I have done those steps, I need to each time say, okay, just enable the first channel. Uh, but if by default that the second channel is not unlocked, this step is not necessary. You also can define the hardware gain and TX gain and RX gain. You can in the video top right, you can see how I configured the ADAM Pluto right now. What we want to do is we want to create a sine wave at our TX, and then it's sent via the antenna and receive in the receiver, and we want to see what's the received spectrum. Then I set the TX hardware gain to -20. You can change this gain. Uh, in RX side, you also have more ability. You can, for instance, set the gain manually, saying 20 dB. In the RX channel, in the RX chain, you have a variable gain amplifier. This is a circuit that you can change its gain by changing its gain code, right? So you can set it to manual, then you set it the gain at 20 dB. But in some scenarios, you don't want to use the fixed gain settings. What you want to do is you want to have a certain power after your VGA or your variable gain amplifier, no matter of what you have at your input. So the gain of the amplifier needs to change all the time to make the amplitude after the variable gain to the value that you define. This is a useful feature when you build actual radios. If the if you, for instance, you can talk with your cell phone while you are walking, and when you are walking, the received signal power is changing constantly. So what you need to do is that you need to have a variable gain amplifier that always tries to control the gain by some feedback loop to have always have certain amount of amplitude at the input of the ADC. Then we create a time vector. Time vector needs to be defined based on your sample rate, because if your sample rate is set to 1 megahertz, your DAC output changes every 1 microsecond, which is 1 over 1 megahertz. So you need to create a time vector with the amount of your number of sample every 1 over sample rate. So once you have the time vector, you need to create the TX signal. As I mentioned in the previous video, because ADALM Pluto sends and transmits both I and Q signal, you not only can send the amplitude, but you also can send the phase information when you are transmitting. So you need to create a complex vector when DL to generate the I and Q. So you set the TX amplitude, then multiplied by E by power of J2 pi F, which is omega t. As you know, E by power of J P is cosine of P plus J sine of P, right? So this is a complex vector which is essentially your which is essentially your I and Q signal. Therefore, using this method, you not only can send the amplitude, but you can send the phase. For instance, you can add a phase here, which we'll talk about in next videos when we want to generate modulations based on phase to also transmit the phase, right? So now we just say SDR the TX signal. That transmits the TX signal. I have two functions. One is compute a spectrum, one is detect topics. A compute a spectrum just once the received signal in baseband is there, we just use this to take the FFT of the signal. One more thing here is that when we are taking the Fourier transform of a signal, Fourier transform usually logs a periodic signal. Otherwise, it may generate some tones that are not necessarily in your spectrum. So windowing can be used to help smooth that behavior, and I used Hanning window here. There are some plotting here, but the one that I want to talk about is the RX part. Same as TX, we just need to say str.rx to get the RX data, right? So first I read it 4 times to clear the buffer and then read it one more time. Again, because this is 2 channel SDR, I just read 1 channel. Then normalize the data to within 0 to 1, because the ADC is an 12-bit ADC, so I need to scale down the data, right? Then compute the spectrum. Let me run the code here. Okay, so this is the spectrum I'm getting after running the code. You can see right now at 1.6, which was the frequency of our test signal, I'm seeing minus 46, minus 47, which is by setting the TX gain to minus 20. So we have minus 20 here. Our RX manually was set to 20. And also we have the attenuation due to air or the PCB. Definitely this number needs some calibration too. But let's see if I change the TX gain, if the this the this peak at the spectrum also changes. Let's say I will make it to minus 10. Okay, great. You see, like it was minus 46, minus 47 before. Now I'm reading minus 36, minus 37. So it's 10 dB higher. Let's go the other way. Let's set it to minus 30. Great. Yeah, minus 56, minus 57, which is 10 dB below the original data. There you have it. This is the spectrum analyzer using the first approach. You can see we can very well read the power of of the received signal, the shape of it, the frequency, contents, and etc. In future videos, uh, we will try the second approach, the other approach using locking amplifier, and also move on to some modulations using ADALM Pluto. Thank you.